As part of my ongoing exploration into machine learning, I recently discovered Battlesnake, a competitive online game where players develop algorithms to control their snakes, vying to see who can survive the longest. In this video, I'll demonstrate how I utilized deep reinforcement learning to train an agent for the game, ultimately achieving a rank in the top 25, 90th percentile of players. The rules of Battlesnake are straightforward. Your snake must remain on the board without running off or colliding with any other snake body, including your own. Additionally, you start with 100 health, which decreases with each move and can be restored by consuming pellets to grow longer. In a head-to-head collision with an opponent, the longer snake prevails. While this might seem straightforward, effective strategies can be counterintuitive. For instance, although consuming many pellets will increase strength for head-to-head collisions, it will also make it harder to avoid colliding with your own body. Players must also code their strategies in advance, because once the game begins, your web server only has 500 milliseconds to respond each turn, making manual play impossible. Most players rely on handcrafted heuristics and tree search, while some incorporate machine learning. I opted to utilize Q-learning, a model-free reinforcement learning algorithm for my approach. This algorithm aims to learn the value, or quality, of taking an action at any state of the game. The concept is that once this value is effectively learned, playing an optimal game becomes straightforward. Simply select the action that yields the highest value at each turn. At the heart of this algorithm lies the Bellman equation, a fundamental concept in dynamic programming, which calculates the value of taking action A in state S as follows: the immediate reward for the action plus the discounted value of selecting the best action in the subsequent resulting state, S prime. There are numerous considerations when determining rewards for reinforcement learning, almost constituting its own field, and after extensive experimentation, I opted to assign my agent -1 point for losing and +1 point for winning. To train an agent, it must first be capable of observing the game state. Battlesnake communicates this to your web server via JSON, and so I initially began by converting that to a single-channel grayscale image, and using a convolutional neural net to extract relevant features from it. This initial approach got me into the top 100, but I soon recognized the need for a more robust observation method. After discovering Arthur Firmino's Battlesnake gem environment and reading Corey Binnersley's related article, links in the description, I switched to a modified 13-channel 11x11 image representation for better accuracy. This is the architecture of my CNN. It comprises 4 convolutional layers with decreasing kernel size and increasing depth, followed by 3 fully connected dense layers. I've opted for leaky ReLU as the activation function. I also upgraded from using a vanilla DeepQ network to a double DeepQ network. This approach employs a second copy of your network, the target, that lags slightly behind the primary online network, and is used to reduce overestimation bias and improve stability. Another improvement I made was to orient my observations so that the agent snake is always aiming upward. This worked because I realized during training that scenarios would potentially have to be encountered 4 different times due to the agent's orientation. Leveraging the board's symmetrical nature, I implemented rotation to reduce the state space, thus improving learning efficiency from the replay memory. After noticing that the agent sometimes lost due to occasional missteps leading to dead ends, I implemented a 1-step look-ahead to prevent such moves unless no other options remained. This adjustment enabled the agent to stay in the game and survive the occasional bad move. Let's now discuss the results and some strategies the agent has learned. As of now, our agent has achieved a ranking of 25 out of 260 total competitors. It consumes pellets at a steady pace, aiming to maintain a similar or slightly longer length than the opposing snake. It also effectively drives opponents off the board whenever circumstances permit. Looking ahead, these are the avenues I'd pursue to enhance performance with additional time. Firstly, implementing prioritized experience replay, as it has been demonstrated to enhance sample efficiency even more. Secondly, allocating any remaining time within the 500 millisecond inference limit to extend the look-ahead to end moves. Given the agent's consistent execution within 50 milliseconds, this adjustment would likely yield the most immediate impact by further mitigating occasional costly mistakes down the line. I've provided links to all the sources referenced or utilized in my journey, along with the hyperparameters that yielded the best performance. Please feel free to reach out if any of this information provides useful in training your own Battlesnake agents. Thank you for watching.